Hello, this is Professor Kuehn, and welcome back to my lectures on space, time, and motion, where we are talking about Einstein's theory of relativity. Last time, we derived the equation for time dilation. We did that by considering the ticking of a clock as measured by an observer who is at rest with respect to the clock. That would have been, I think it was Luke riding in a spaceship in my last lecture, compared to the time between the ticks of that same clock as measured by John, who is watching the clock rush by very quickly. Let me remind you what the formula for time dilation is. So this is the topic of time dilation, and the formula is delta t equals gamma times delta t naught. And remember, the idea of time dilation is that moving clocks tick slowly. And this is the formula, delta t equals gamma times delta t naught. And remember that gamma is defined as 1 over 1 minus v squared over c squared square root. And just to remind you what these various quantities are, well, remember that v is the velocity or the speed of the clock compared to the observer. Okay, and c is the speed of light in a vacuum. So if you know the speed of the clock relative to the observer, that's v, and the speed of light in a vacuum, 3 times 10 to the 8th meter per second, it's very simple to calculate gamma just by plugging into this formula. You can then plug that into this formula and find the relationship between delta t and delta t naught. Those are the time between ticks of that clock as measured by various observers. Now, the difficulty in solving problems like this always has to do with identifying which observer is measuring delta t naught and which one is measuring delta t. If you can identify that, you can solve problems like this. So let's just go through and define what we mean by delta t naught and delta t. I'll give a kind of a formal definition of each of these, and then we'll work out a problem to show how this kind of thing works out. So what do we mean by delta t naught? So I'm just going to state it here, and I'm going to write it down. Delta t naught is the time between two events, like ticks of a clock, the time between two events as measured by an observer who sees those events happening at the exact same location. So it is the time between, or the time elapsed between two events. Think ticks of a clock, or perhaps the snapping of my fingers. The time between two events as measured by an observer who sees or witnesses, who sees the events occurring or happening at the same location. And that, in our case, would have been Luke in our previous example, the person who's riding on the spaceship and sees the clock right in front of him. So remember, in that case, let me draw a picture here. We had Luke riding on the ship, and we had this light clock where light was bouncing back and forth between these two mirrors, and each time the light hit the bottom mirror, it would tick. So if you think about from Luke's perspective, the events would be each tick. So event 1 would be tick 1, we might say. Event 2 would be the next tick. And the question is, if we look at those events, if Luke is looking at those two events, are they happening in the exact same location according to him? And the answer is yes. So if he set up a coordinate system in his ship, let's say an X and Y coordinate system, those ticks are both occurring at the exact same X and Y coordinates. So those events are happening at the same location, and so he would be measuring delta t naught. This is sometimes called the proper time. Not in the sense that it is the correct time. Remember, the theory of relativity claims that there's not a preferable observer or a preferable reference frame. It's called the proper time for perhaps unfortunate reasons, but think about proper meaning his own time, okay? I think if you're in doubt, just go back to this definition right here, okay? Then what is delta t? In this formula for time dilation, delta t would be the time interval between those same two events as measured by an observer who sees those events not happening at the same location. Or rather, maybe we could put it this way, the time between the same two events as measured by an observer who is in motion relative to this first observer. I'll write it the first way I said it. The time between the same two events as measured by an observer who does not see the events occurring at the same location. So, which of the observers in our previous example would be measuring delta t? Well, remember, in this example, we had Luke. Again, he's watching this, the light bouncing back and forth between his mirrors. And then we had John, who is sitting out here. This is John. And in the example, the spaceship was rushing past. And so what happens if we think about subsequent moments in time, the first event would be when the light leaves the bottom mirror, and the second one would be when it hits that same mirror once again. So remember, the light moved up, bounced off the top mirror, and came back down, and so you have two ticks. The first tick would be here, according to John, and the second tick would be over here at a different location. So these would be the same two events, event 1 and event 2, but they do not happen at the same location, according to John. And so he would be measuring delta t. Okay? So what the theory of relativity, and specifically what the theory of time dilation, allows us to do is determine the relationship between the time interval between those two events as measured by one observer and another observer. Okay? So in other words, if there was a, let's say, a 1 second interval between ticks according to Luke, if the spaceship is going by at some speed v, we could calculate gamma. We could put in 1 second for the time between those events according to Luke, and we could calculate the time between those two events as measured by John. Okay, we'll do an example in my next lecture, but let me just say something else about gamma. I want to give you a little bit better understanding of what we mean by gamma. So let's make a plot of the gamma or gamma factor as a function of the speed of the ship. Okay, and I'm going to mark off C right here, and I'm going to put in a little asymptote right here. What does the function gamma look like as a function of velocity? Well, you might see by looking at it that when the velocity of the ship is 0, you have 1 minus 0, which is 1, and so gamma is going to be equal to 1. So when the speed of the ship is 0, then gamma is equal to 1, right there. What happens as the speed of the ship approaches the speed of light? Well, v approaches c, so you have c squared over c squared, which is 1. 1 minus 1 is just about 0. So what's going to happen is this function is going to blow up. It's going to asymptotically become infinity as the speed approaches the speed of light. So what does gamma look like? It's going to be increasing like this and approaching asymptotically infinity as the speed gets faster and faster. What is this telling us? This is telling us that at very low speeds, if the ship is moving very slowly, or in fact if the speed of the ship is 0, then gamma is going to be 1, and you're going to find that delta t is going to be the same as delta t naught for the velocity equals 0. This is consistent with our common sense that for observers who are at rest with respect to one another or moving at very low speeds compared to one another will agree on the time intervals between ticks of a clock that they're both observing. What's unusual now that's introduced by Einstein's theory of relativity is that as the speed increases, and in fact as it's closer and closer to the speed of light, they're going to disagree with each other more and more about the time interval between the ticks of the clock, or more generally, the events that they're measuring. This, by the way, is only a very pronounced effect. In other words, you're not going to notice this difference unless someone's moving very near the speed of light. And this is precisely why this kind of effect, according to Einstein, was missed for so many years.